Let's go into information theory coding and some basic algorithms for entropy, probability, and binary compression. First, we will start with entropy. What is entropy? Entropy is the average uncertainty of a random variable. A distribution with low entropy is predictable. A distribution with high entropy is unpredictable. The maximum possible entropy for a variable with X outcomes occurs when all outcomes are equally likely, also known as the uniform distribution. Let's adjust the entropy probability outcome for A with a 3 possible variable solution. With outcome C fixed at 20%, the entropy changes as the probability distribution shifts. The reason entropy is displayed in bits is directly tied to the mathematical formula used to calculate it and what that formula represents. A logarithm's base determines the unit. With the given formula for entropy, the crucial part is the base of the logarithm. By convention in information theory and computer science, the logarithm is base 2, resulting in a unit of information called a bit. Fano's inequality relates the average information lost in a noisy channel to the probability of the categorization error. It was derived by Robert Fano in the early 1950s. Fano's inequality gives us a hard limit on our ability to guess a random variable x, even if we have information from a related variable y. It connects the remaining uncertainty to the probability of making an error. If your probability of error, p, is low, the right side of the inequality is small. This forces the conditional entropy h, xy, to also be small, meaning you must have low uncertainty about x given y. You cannot have a low error rate and high uncertainty simultaneously. This chart shows how the maximum allowable conditional entropy, the Fano bound, changes with the error rate. If your actual h, xy, is above this bound, the situation is impossible. Now, let's get into the language of codes. A code is a system for translating symbols from one alphabet, like English letters, into another like binary digits. The goal is to create a representation that is both efficient and, crucially, unambiguous. Simply assigning a unique binary string to each symbol isn't enough. When we concatenate code words, we can create ambiguity. This is the core problem that leads to the study of different code properties. Ideally, every sequence of symbols maps to a unique encoded string, and no code word is a prefix of another code word. This is a much stronger condition that makes decoding incredibly simple and fast. This is the minimum requirement for a useful code. We can visualize a binary code as a binary tree. Each edge represents a bit, 0 for left, 1 for right. A code word corresponds to a path from the root. Here we show a prefix code tree versus a non-prefix code tree. On the prefix code tree, all code words are at leaf nodes, such as you cannot continue a path past a code word. A non-prefix code tree uses code words as internal nodes on paths, leading to ambiguity of possibilities. Let's try decoding this non-prefix code. We can tell A is 0 by following the path of the first bit 0. The B, represented by 0, 1. This means you follow 0 and then 1 to arrive at the code word. We follow this same pattern for the rest of the code tree to decode the code word from the binary data. Let's try this string. After the first 0, we notice no further available paths. This means the next bit starts the process over again, leading to backtracking. We can decipher the code, now knowing these rules. It's ACD. You can't know the first 0 isn't a until you process the rest of the string, causing a decoder to have to backtrack. This lowers efficiency and increases ambiguity. We want our codes to be unambiguous, but also efficient. An efficient code uses shorter code words for more frequent symbols, minimizing the average length of an encoded message. The Kraft-McMillan theorem tells us the mathematical constraint that all UD code lengths must obey. This connects the property of unique decodability to code word lengths. Crucially, it also proves that for any set of lengths that satisfies this inequality, a prefix code can be constructed. This means we lose no efficiency by restricting ourselves to easy-to-decode prefix codes. We provide a binary code word inequality checker, to experiment with. This allows you to explore different code word lengths to see how they would be constructed. While the Kraft-McMillan theorem is an existence proof, the Huffman algorithm is a constructive proof, a simple, greedy algorithm that creates an optimal prefix code for a given probability distribution. The algorithm repeatedly merges the two least probable symbols into a new meta-symbol, building a binary tree from the leaves up to the root. Here we provide an interactive Huffman coder. You can enter symbols and their frequencies or probabilities. The tool will generate the optimal Huffman code. Be sure to check out the GitHub for code examples and to download this interactive tutorial to keep exploring this topic further.